Alright, so in this lesson we are going to look at equations of motion for objects that are under constant acceleration. Yeah, we are going to come up with a set of equations that we can use in situations where objects move under constant acceleration. And what we mean by constant acceleration is that the velocity of that object changes at a steady rate. Yeah, so that means, for example, if an object's velocity increases by 5 meters per second every second, and it continues to do that, then as long as it's increasing, or it can even be decreasing, as long as the velocity is changing at a steady rate, we can consider that to be a constant acceleration. Even if there's no change in velocity, even if it's traveling at constant speed, that is also technically a constant acceleration of 0. Yeah, so as long as the velocity of the object changes at a constant rate, it's a constant acceleration. And you have to recall that the velocity time graph for a constant acceleration is a straight line, because remember, the gradient of this line gives the acceleration. So here, for example, we have on the graph on the left, we have a positive constant acceleration, and on the graph on the right, we have a negative constant acceleration. Or you can even consider that to be a constant deceleration. Also, always remember what this means. This means that for a given amount of time, the velocity changes at by for a given amount of time, the velocity changes by a specific amount. So, for example, I can choose a specific time interval like this. Then the change in velocity will be this amount, and if we select that same time interval at some other place, it's not a very good drawing, but then if you find the same time interval, so maybe something like this, yeah, then that would also give the same increase in velocities. I know my lines are not very straight, so it's a little bit different, but I hope you get the point. For a given interval of time, the change in velocity is the same, because that's what we mean by saying that the acceleration is constant. Right. So when we deal with calculations involving uniformly accelerated motion, there are 5 quantities that we deal with, and these 5 quantities are the initial velocity of the object, that we give the letter u to it, the final velocity of the object, we give the letter v to it, acceleration, letter a, time taken for the velocity to change from the initial to the final velocity, we call that t, and the displacement that happens during the time t, we call it s. So these 4 symbols are the symbols that we are going to use to come up with our equations. So there's 5 equations. Sometimes you only consider 4 equations, but you can come up with 5 of them. So I have all 5 of those equations right here. And in each of these equations, one of the quantities is missing. Yeah. So each equation has 4 of these quantities, and if we know 3 of these, then we can use the equation to find what the 4th quantity is. So the equations we have v, that is the final velocity, is equal to u, initial velocity, plus acceleration times the time, and we have s is equal to half times u plus v into t. S is equal to ut plus half at squared. S is equal to vt minus half at squared. V squared is equal to u squared plus 2as. So these 5 equations are the equations that we are going to use when we deal with problems where objects are moving at constant velocity, at constant acceleration. These equations are also called the suvat equations, because you can see that the letters, the symbols that are used in these equations are S, U, V, A, and T. So now we plan to derive these equations to see where these equations actually come from. So let's first start with the equation V is equal to U plus AT. I'm trying to derive this equation. How do I begin? Well, we start with the definition of acceleration. Remember, acceleration is final velocity minus initial velocity divided by the time taken. Yeah, this is a change, because acceleration is a change in velocity divided by the time taken. Yeah. So then I can rearrange this equation and make V the subject of this equation, and that gives me V is equal to, so let me do it in two steps because otherwise it will be too simple. So we get AT is equal to V minus U. So I can again rearrange this to make V the subject. So that will be V is equal to U plus AT, which is exactly what we wanted. So I'll call this the equation number 1. Right. And then I'm trying to derive the next equation, which is S is equal to half U. S is equal to half U plus V into T. So there's two ways I can consider deriving this equation. First way is to consider the meaning of average velocity. The average velocity of an object. I'll write it like this. The average velocity, let me actually write it down. So average velocity, very good. So average velocity, I will give average velocity with a symbol like this. Yeah, the average velocity is equal to the total displacement divided by the total time taken. Yeah. So I can say in that case I can rearrange this equation to get S, to make S the subject. So S will be equal to just the average velocity times the time. Yeah. But what is average velocity of a constant in a case where the object is accelerating constantly? Whenever we have a quantity that is changing at a constant rate, then the average, so the average of that quantity, the average of that quantity is the midpoint between the starting value of that quantity and the final value of that quantity. So for example, if the object is accelerating at a constant rate, and it starts with an initial velocity U, and then it goes to a final velocity V, the average velocity would be the halfway point between the initial velocity and the final velocity. Yeah. So in that because of that, I can write the average velocity V as the halfway value between U and V. So it's essentially the average of the value of U and V. Yeah. So because I can write it this way, then because of this I can take this equation, and I have an expression now for the average velocity. So I can put this instead of this into this equation, and then I get S, oops, it's the wrong color, I have to get black. So S is equal to half U plus V, because that is what I have for average velocity. Yeah, and that is equal to the average velocity, and then it was average velocity times time. So now I have to add the factor of T outside here. and this is what I want to find. So I get the so I get now the second equation. Or alternatively, I can also arrange this come to this equation by looking at the graph of by looking at the velocity time graph of an object with uniform acceleration. Again, because it has uniform acceleration, it's going to be a straight line. So in this case, the initial velocity of the object, I can mark that on the graph as u. This is the initial velocity of the object. And the final velocity of the object, I can mark that as v. And the time taken for the object to go from this initial velocity to the final velocity is t. And by looking at this graph, I can say the displacement is the area under the graph, because it's a velocity time graph, and in a velocity time graph, the area under the graph gives you the displacement. So displacement here is the area under the graph. So it may be, so what I mean is this area here, yeah, this area of this part under the graph, that will give you the displacement during this time. So because it's a trapezium, should I remove that scribbling? Yeah, I'll probably remove it. Because it's a trapezium, I can say the area under the graph is half into u plus v into t. Where does that come from? Because the area of trapezium is usually, if you have a because when we consider this as a trapezium, yeah, the area is given by half times this length times, sorry, this length plus this length. So that is essentially u plus v, and I have to multiply that by this length, which is t. So that's how we got to that equation. Yeah, and because s is equal to the because s displacement is the area under the graph, I can just now I can just say displacement is equal to half u plus v into t, which is again the equation that I wanted. Yeah. So you can use either of these methods to confirm that confirm the second equation. S is equal to half u plus v into t. Of course, this can be written in different ways. So some people will write it like s is equal to half. Some people write it as s is equal to u plus v t divided by 2, but it's the same thing. It's just a different way of writing it. It looks different, but it's just the same thing. Then we go to another equation. We are trying to derive now s is equal to ut plus half at squared. Yeah. Okay. To do this, I need the first equation that we derived, and the first equation that we derived was v is equal to u plus at. And I also need the second equation that I derived, and the second equation is s is equal to half u plus v into t. Now what I do is I know that v is equal to u plus at, so in the second equation I substitute for this v this quantity u plus at. So now what I get, so what I do, let me highlight what I'm doing. So I'm taking this quantity and I'm putting it into this quantity. Yeah. So what I get when I do that is I get S is equal to half u plus at. Yeah. So that is half times 2u plus at, and if you expand this out, you get half times 2u plus half times at. Yeah, and of course half and the 2 cancels out. Yeah, so you are left in the end with the equation S is equal to u plus okay, I'm making some sort of mistake here. I forgot that I have to multiply by t. So yes, I have to have this t at the end. So sorry, I have to change this again. So I had a t here, and then I still have a t here. So that means when I have the t here, when I have the t here, when I multiplied by 2u, I get half times 2ut here, and then when I multiply at by t, I get at squared. So I should have at squared here. So now it makes sense. So now I get when I cancel the first part, I get ut. So now I have ut, and then plus I have half at squared, and this is my third equation. Okay, next one is very similar, but here what I do is, instead of taking I take the first equation, but which is v is equal to u plus at, I make u the subject of this equation. So u is equal to v minus at, and I substitute for u in the second equation. So what I'm doing is, I know from second equation S is equal to half u plus v into t. So what I'm now doing is, I'm taking this value for u and I'm putting it instead of this u in the equation. Yeah. So what do I get when I do that? When I do that, I get S is equal to half, instead of u I'm writing v minus at, and then we still have the plus v inside the bracket, and this time I won't forget the t. I have the t also in there, and then I can add the two v's inside the bracket. When I do that, I get half 2v minus at, and I still have the t outside. Yeah. So what happens now is, I get half times 2v minus half times, no, still wrong. For some reason I just keep forgetting that t exists here. So maybe I'll use the next line for this. So I'm probably running out of space here. Right. So I can say S is equal to half times 2vt minus half times at squared, and like we did earlier, this 2 cancels with this 2, leaving you with S is equal to vt minus half at squared, and this is the fourth equation that I was looking for. To get the second equation, to get the final equation, we use the first and second equation. So the first equation was v is equal to u plus at, and the second equation was S is equal to half u plus v into t. Yeah. So what I now do is I will make t the subject of this equation and substitute that t into the first equation. So let's do that. So how do I make t the subject of this equation? I get t is equal to 2s divided by u plus v. Yeah, and this value of t I can now substitute back into the first one. So I will show what I'm doing like this. So I have t is equal to 2s divided by u plus v. So I'm just putting that into the first equation instead of t. So what happens when I do that? Then when I do that, I get v is equal to u plus a, instead of t I'm having, remember, 2s divided by u plus v. So I can now write it as, okay, let's first write it like this: u plus 2as divided by u plus v. How do I add these two together? Now, because these are algebraic fractions, if I want to add them, I want to make this, the denominator of this, also to be u plus v. How can I do that? I have to multiply both the top and the bottom of this by u plus v. So what happens when I do that is I get u times u plus v divided by u plus v is equal to, sorry, not is equal to, and the plus, the rest of it I get plus 2as divided by u plus v. And now because the denominators are the same, because the denominators are the same, I can just add these two things together. So how does that work? Now I get u plus v, the big denominator. Remember, all of this is equal to v still, yeah, and this big denominator plus on the top I get u plus v plus 2as, and let me multiply both sides by u plus v. Then I will get v times u plus v. So this implies v times u plus v is equal to u times u plus v plus 2as. Right, now I can expand these brackets, and what I get when I expand the brackets is I get vu plus v squared is equal to u squared plus vu plus 2as. Now I can subtract from both sides vu. If I subtract vu from both sides of the equation, I get, so I'm going to subtract from both sides of the equation, I'm going to subtract vu. What I get when I subtract vu from both sides of the equation is v squared is equal to u squared plus 2as. So this v squared is equal to u squared plus 2as is exactly what we wanted. So now this is our fourth equation. Sorry, not the fourth equation, but rather the fifth equation that we wanted. Yeah. So now we have derived all of our four equations of not four, but rather 5 equations of motion. So now we look at how to actually use this in problems. To use these equations in problems, first of all we'll consider cases where objects move in one dimension. So that means they're moving in a straight line. Yeah, they can go up, they can go down, they can go left or right or diagonally or whatever it is, but they move along the same line. If they're moving if the motion is not along the same line, the process is a bit more complicated, but we'll be dealing with those things at a later time. So we look at using these suvat equations to solve problems in one dimension. Okay, so to solve these equations, what we usually do is we establish a direction to be the positive direction. So any of the vector quantities, that is initial velocities, final velocities, accelerations, displacements, any of those things that is along the direction that you declare to be positive, you have to write as a positive vector. Any vector quantity that is in the opposite direction, you have to write as a negative vector. And it doesn't really matter what direction you choose to be the positive direction. There are conventions where you use always upwards to be positive and downwards to be negative, for example, and to the right to be positive and to the left to be negative, but you don't have to stick to that. All you have to worry, it's okay if you stick to that. If that makes your life easier, that's perfectly fine, but be aware that it's not wrong to say, for example, that downwards is the positive direction. As long as you are consistent with the directions that you use in your calculation, your answer will be consistent with the rest of the calculation. That's all that matters. Yeah, and the direction, the choice of what to call positive should be up to you, and that should depend entirely on your convenience. And pay attention to the description of the problem. So if you see that an object is falling freely, then it has a constant acceleration of 9.81 meters per second squared towards the ground. Yeah. And if a question says that an object is dropped, for example, rather than thrown, then the initial velocity of that object is 0, because you're just dropping it, you're not throwing it. So at the start, the object has a velocity of 0. And also it's good to keep in mind that these equations can be only used in situations where acceleration is constant. If not, you can't use these equations just in any other situation where there is motion. Yeah, the acceleration has to be constant. So let's take one example. So we have a stone is dropped from the top of a well that is 11.5 meters deep. How long does it take for the stone to reach the bottom of that well? So we can imagine, it always helps to draw a small diagram. So we have a little well. So let's say this is the well, and you're dropping it. Not a very nice well, but okay. You're dropping it, and then the well is 11.5 meters deep. Yeah. How long does it take for the stone to reach the bottom of the flow? So what we need to first identify is what are the quantities that we know. Okay, I know that they say the stone is dropped. If the stone is dropped, then I know the initial velocity is 0. So then I can mark that, okay, I know initial velocity of the object, and I know the displacement of the object. Yeah, I know the displacement of the object at the end of this motion. So then I also know that my S is equal to 11.5. So I'll mark it here that I know my S is 11.5. Then what else do I know? This stone is dropped and it's just freely falling. So then I should know that the acceleration is equal to 9.81. So let me also define downwards to be positive. If I say downwards direction is positive, then the acceleration, because the stone is accelerating towards the ground, it will be a positive value, and the displacement will also be a positive value because the object has moved downwards. So all of these values will be positive, and actually I won't have any negative values in this equation. Yeah. So I know 3 quantities, and I'm interested in the 4th quantity. How long does it take for me to know? So I know acceleration, I know my acceleration, and T is the quantity that I'm interested in. I want to know what T is. Yeah. So now what I need to do is I want to find what t is, and I want an equation that has these quantities s, u, a and t. That is the equation that doesn't have a v. So which one is that? So that would be I can take s is equal to ut plus half at squared. Yeah, and I want to find t. So remember, so I take equation s is equal to, yeah, so I taking s is equal to ut plus half at squared. Notice that u is 0. So if I put 0 into this equation here, this entire thing u times t will just be 0. No? So I can just, because u is equal to 0, I can get rid of this factor because u is equal to 0. That whole thing just goes off. So what I'm left with in the end effectively is that s is equal to half at squared, and t is the quantity that I'm interested in finding. So I'll rearrange this equation and make t the subject of it. So what do I get when I do that? I get s is I want to make t the subject. So t is equal to 2s divided by a, the square root. Yeah? And we are taking the positive square root, of course, because time can't have a negative value. Yeah. So then I just substitute the values into the equation. So then this is square root of 2 times what is s, the displacement, and the displacement is 11.5, and the whole thing I have to do by acceleration, that is 9.81. And what do I get when I do that? So 2 times 11.5 divided by 9.81, that gives me a value of 2.34, and this in seconds. So it takes 2.34 seconds for the stone to reach the bottom of the well. Okay, in the next part of the question they ask what is the speed of the stone when it reaches the bottom. So from the earlier part of the equation we established that we knew u, s and a. Yeah, so let me mark that again here. You don't have to always draw something like this, but I'm just drawing it because we are doing it for the first time. So so s is, yeah, I know s, I know u, I know a, and this time I'm interested in finding the final speed of the stone. Yeah, so I need an equation now that has these 4 quantities s, u, v and a, and that is the equation without a t, and that one is, when I look at these equations I find that it is v squared is equal to u squared plus 2as. That's the equation that I want to use. Yeah, so then I can write, I'm using v squared is equal to u squared plus 2as. Yeah, and so that means I'm interested in v, so that will be the square root of u squared plus 2as, and therefore v is equal to square root of u is 0, so u squared will be 0, 2as will be 2 times, so I'll write it here itself, so that's equal to square root of 2as, because in this particular case u is equal to 0. So 2 times 9.81 times s, that is 11.5. How much is that? Oops, that's the wrong answer. So 2 times 9.81 times 11.5, square root of that, I get 15.0 meters per second. This is the speed of the stone as it reaches the bottom of the well. Right. So let's look at another example. So in this example, a ball is thrown vertically upwards with a speed of 8 meters per second from a height of 1.5 meters above the ground. How far above the ground does the ball rise? So say this is the ground. Get a straight line. So it's the ground, and somebody is throwing the ball from a distance of 1.5 meters. So this is the distance of 1.5 meters. And the ball is thrown up. So the ball is going to go up. It will reach the top, and then it will come back down again. Yeah. Okay. So I'm interested in how far of the first part. I'm interested in how far above the ground does the ball rise. So that means I want to find out this height. Sorry, I want to find out this height, because I'm asked for the height above the ground. Yep. So what I will do is I will try to find out this displacement from the starting point. How far does it go to reach the top? That's the displacement. No, I can consider the motion from this point up to this point, and then I can find the displacement that the ball gets through from the point it was thrown up until it reaches the top of its path. Yeah. Okay. So what are the values that I know? I know that. So let's start again. This time by making upwards positive. I'll make upwards the positive direction. So I'll put a little arrow, something like that, to indicate that I'm taking upwards direction as the positive direction. So in that case, my initial velocity, which was upwards, will be plus 8. What are the other quantities that I know? I know that I'm considering the motion from this point to this point now, from the point it was released until it reaches the highest point. So when it reaches the highest point, it will come to a momentary stop. No, it will slow down from the moment it was thrown up, and it will come to a momentary stop when it's at the top of the when it's at the top. So at this point, if you consider the motion from here to here, the final velocity at this point would be 0. When it reaches the top, momentarily its velocity is 0. And all this while, this ball is under constant acceleration from the ground, and it's constantly accelerated towards the ground with an acceleration of 9.81. So because I define my upwards direction as positive, this acceleration, I have to give it a negative value, because that acceleration is acting towards the ground. So I have to write it as minus 9.81, because it's under constant acceleration, but that acceleration is towards the ground. And I have said in this question the upward direction is positive, so then my acceleration will get a negative value. And of course, the quantity I'm interested in now is this quantity S. What is S? So I know U, I know V, I know A, and I want to find out what S is. So what's the equation I can use here? Once again, V square is equal to U square plus 2AS. So let me write that. So we get the equation of choice is V squared is equal to U squared plus 2AS, and we know that V is equal to 0, so we just get well, I can say (2AS). We can just say so we can say 0 is equal to U squared plus 2AS, and then S I can make the subject, and that would be minus U squared minus U squared divided by 2A. Yeah, that's what happens when I make s the subject of the equation. So what is that? So minus u squared would be minus 8 squared divided by 2 times my acceleration now has a negative value, so I have to write it as negative 9.81. Yeah, so this is 8 squared is minus 64, and at the bottom I get 2 times 9.81, that is 19.62, and so 64 divided by 19.62, I get 3.2 3.3. Let's write 2. So there's 3.3 meters. That is my displacement. So the ball rises 3.3 meters above the ground, because what I'm getting is this quantity here. This displacement is 3.3 meters. So sorry, it doesn't really rise 3.3 meters above the ground. It rises 3.3 meters from the point when it was released. But again, because I'm interested in the distance from the ground, this height h, so h is equal to 1.5 plus 3.3, and that is 4.8 meters. So if I'm measuring it from the ground rather than from the point where the ball was released, the height the ball rises to is 4.8 meters. Okay, let's go back to another question, to another second part of that, and that part says if the thrower doesn't move, how long after throwing will he catch it? So assume the thrower catches it at 1.5 meters above the ground. So again, let me draw a very quick diagram of that earlier case. So you have the ground, and then you are throwing a ball from a height of 1.5 meters above the ground. And then what happens to the ball? The ball goes up. When you release it, so the ball goes up and it will reach the top, and once it reaches the top, it will come down, and at some point it will come back to the same level. Yeah, and when it comes back to the same level, because they say that person is catching it at 1.5 meters above the ground, so it's coming back to the same level. So now I want to find out the time it takes for the ball to come back to the same level. So I'm considering the motion now from the point it was thrown up, until it comes back to the same place. For that time period, u is still, so let me still call upwards my positive direction. So u is still 8 meters per second. And I know that there's a constant acceleration towards the ground, a negative acceleration of 9.81. The other quantity that I know is that when it comes back to the same position from the time it was thrown, the displacement of the ball is 0. Yeah, because it's at the same level back again. So the distance between the initial position and the final position is 0. So the displacement of the ball is 0. And of course, I'm interested in the time. What's the time it takes for this to happen? So now I know the quantities u, a, and s, u, a, and s, and I'm interested in t. So which equation do I have to use? The one without v, and that would be s is equal to ut plus half at squared. So now I use s is equal to ut plus half at squared. So s is equal to ut plus half at squared. and I know that my s is 0, so I can write, oops, 0 is equal to ut plus half at squared. So now I can fact this a bit of a quadratic type of equation, but I can solve it without using the quadratic formula quite easily if I factorize it. So I take t out, so 0 is still here, I take t out of the equation, so I get u plus half at is equal to 0. So this happens either when, so either t is equal to 0 or t is equal to u plus half at. Sorry, either not t, this is wrong. Why isn't erasing? Oops, sorry. So you get t is equal to 0 or u plus half at is equal to 0. Now t is equal to 0 is right at the beginning, and of course this makes sense because right at the beginning, when you throw it, the displacement is 0. Yeah, the ball hasn't moved at all yet, so at the beginning, at time t is equal to 0, the displacement is 0. But this is not the result we are interested in. We are interested in this part, and this, when I solve this equation for t, that will give me the time when the ball is once again at 0 displacement, and that is the time I'm interested in. So let me try to solve that equation. So then I get yeah, so then I get t is equal to, let me again do it in a couple of steps rather than trying to do it straight away. So I can say half at is equal to minus u, and that means t is equal to minus 2u divided by a. So now I can substitute the values into the equation. So I get minus 2 times u, that was 8, divided by a, and remember a is minus 9.81. So what do I get when I do this? 2 times 8, that is 16. 16 divided by 9.81, I get a positive value of 1.63. So the time it takes is 1.63 seconds. For the ball to come back to the bowler, it takes 1.63 seconds. Now, the next part says if the thrower moves away immediately after throwing. Yeah, so the thrower doesn't try to catch the ball just falls to the ground. And in this case, how long does the ball take to fall to the ground? So once again, we'll draw a diagram. So you have the ground, and the ball is thrown up from a height of 1.5 meters. So it goes. So the ball will go. Up. So reach from here. So it will go up. It will come to the top, and then it will start coming down. And because there's no player here this time, the ball will go straight to the ground. Yep. Notice that even though I'm drawing this like a curve, the ball is actually falling in a straight line. And of course, I can't draw two lines on top of each other. That's why I'm drawing it like this. The ball is falling to this position. Yep. So now I'm interested in finding out how long does it take for the ball to fall to the ground. So I'm interested this time from the motion, I'll call it A, from the beginning here to the motion until it lands here, from the motion from A to B. Yeah. Now, for this motion from A to B, I'll use upwards once again as my positive direction. Yeah. So what are the quantities I know for the motion from A to B? I know that U is still equal to 8. acceleration is still going to be constantly minus 9.81. How do I relate the position B to position A? And the way I relate it is I look at the distance between A and B, and the displacement at the end of this period would be 1.5 meters. But because the ball was here and it ends up below where it started and upwards is my positive direction, this displacement is a negative displacement of 1.5, because the final position is below the initial position and I've said the upwards is my positive direction, so the displacement now is a negative displacement. If it ended up somewhere here, then it's a positive displacement. If it ends up below where it started, because I say upwards is positive, this is a negative displacement. So here the displacement is minus 1.5, and I'm interested in how long. So I know U, I know A, I know S. T is something I don't know. So now what you do, you search for an equation where you have these four quantities. In other words, this is the equation without a V, and once again it's the same equation we used earlier. It is S is equal to ut plus half at squared. So we get S is equal to ut plus half at squared, and I'm interested in T. So this time 1 minus 1.5 is equal to 8 8t plus minus 9.81. I have to put the factor of half, ut plus half 80 squared, so I have to put that factor of half in here, plus half times minus 9.81 times t squared. Yeah, I will write all of this again much. I can write all of this as minus 1.5 is equal to 8t minus, so 9.81 divided by 2 is 4.91, minus 4.91 t squared, and here we have a quadratic equation. So let me rearrange this into the general quadratic form. So I have an equation that is minus 4.91 t squared plus 8t plus 1.5 is equal to 0. So then we compare this with the general form of quadratic equation, where we have a t squared plus bt plus c is equal to 0. Yeah. So a is minus 9.41, b is 8.0, and c is 1.5. Okay, so then it's a matter of solving this quadratic equation. I'm going to cheat here and I'm going to use the calculator to get values for this quadratic equation. So I'll get two values. So let me enter these values into my calculator. How do I do that? Solve. I'm asking my calculator to solve something, but it's refusing to do that. I think I have to go. Yes, I have to go to equation. Yeah, quadratic. A is minus 4.91. B is plus 8, and C is 1.5. And then one of the solutions I'm getting is 1.5 1.799. So I will write it as so I will write as 1.8 seconds, or my other solution is t is equal to minus 0.17. So out of these two, I am going to have to discard this one because t can't be negative. So I'm discarding that, and then my answer is time is equal to 1.8 seconds. So it takes 1.8 seconds after the ball is thrown for it to reach the ground. So notice that earlier it took 1.63 seconds if the bowler caught it, if the person who threw caught the ball, and now it takes 1.8 seconds for it to reach all the way to the ground. Okay, so we'll do one more question. Well, actually one question in two parts. This one is a little bit more complicated than the other ones, but we'll still try to do it as well. And I didn't this time include these equations on the side because I remember the equations, but if you are confused at any point, you can always look back at the equations and you can see why I'm choosing the equation that I'm choosing. Okay, so the Burj Khalifa building, and that is 830 meters tall, is the tallest building in the world. So there's Linda, and she drops a coin from the top of this building, and there's Terry. He's halfway up the building, and he also wants to drop a coin so that his coin will land at the same time as Linda's coin lands on the ground. Yeah. So the problem is to find out, after Linda drops a coin, how long should Terry wait before dropping his coin? Right. So this is a slightly longer question, but let's try to work it out by breaking it down into different steps. So once again, let's start by drawing a diagram. So let's draw, let's say this is the building. Now, and Linda is here, and Terry is exactly halfway. Yeah. So I know that this height is half of 830, that is 415. So this is 415 meters. And then this is a further 415 meters. Yeah, so this is another further 415 meters. So let's start by finding how long it takes for Linda's coin to fall to the ground, right? So let I write like this. Let TL be time taken for Linda's coin to fall to the ground. Okay, so with Linda's coin, what are the quantities that we know? We know that Linda is dropping it, so it's the initial velocity is 0. Sorry, initial velocity is 0. We know that by the time it reaches the ground, because I'm considering the motion from A, from the point where Linda drops it, that's on the top of the building, this point to this point. So I know the displacement by the end of this motion is 830 meters. So let me make downwards positive also, because here there is nothing in the upwards direction, so I can keep all the downwards as positive, so I won't have to worry about any negative numbers. So S here is positive 830 meters. And I know, of course, there's an acceleration towards the ground of 9.81. I'm going to take it as positive this time because I'm taking the downwards direction as positive. And then I'm interested in the time it takes for Linda's coin to fall. I don't know what it is. So which equation can we use here? I can use S is equal to ut plus half at squared. Yeah. So I use S is equal to ut plus half a t squared. So t of course I call it TL because it's the time for Linda's coin. U is 0, so once again this part just cancels out because when you multiply u by t, it just becomes 0. So now I'm interested in finding t. So I can say the time it takes for Linda's coin to fall. So let's not skip that ahead. Let's again maybe write it once more. So S is 830. Okay, no. So let's say S is equal to half a t squared. So I'll write t squared will be equal to 2s. 2as. Yeah, it's equal to 2as. Sorry, my bad. T squared is equal to 2s divided by a. Yeah, and so that means t will be equal to square root of 2s divided by a. And here is the time for Linda, so I'll always put a little L there. So time for Linda is going to be square root of, let's call this S also, the distance that the Linda's coin has to travel. So let's call it SL, just for the fun of it. So this is the Linda's coin's time. Yeah, so this is Linda's time, Linda's distance. So that is equal to 2 times Linda's distance, that is 830, divided by acceleration, that is 9.81, and the time it takes, you can work this out. So that is 2 times 830, 2 times 830 divided by 9.81, square root of that gives me 13. So time is 13 seconds. So it takes 13 seconds for Linda's coin to fall to the ground. Now what I'll do is, I'll do the same thing for Terry. I'll find how long it takes for Terry's coin to drop to the ground. So let t be equal to time taken for Terry's coin to fall to the ground. From Terry's point of view, now we are considering the motion from this point, from Terry's position to the ground. Yep. So the displacement will be just 415 meters. So I start of course with u is equal to 0 because Terry is also just dropping the coin, not throwing it. The distance that Terry's coin has to move, or the displacement that it has at the end, is 415 meters. It will also be under constant acceleration of 9.81, and I'm interested in finding Terry's time because it's very similar to the earlier question, only the values are different, but only as the values of the distance is different, everything else is the same. So I can pretty much use the same equation here as well. So I'll just say, without doing the first couple of steps which will give me the same result, I'll just say the time taken for Terry is also equal to square root of 2 times the distance that Terry's coin has to travel divided by acceleration. So that is 2 times 415 divided by 9.81. So 2 times 415 divided by 9.81, and I have to take the square root of that, and that will give me 9.20 seconds. No? So Terry's coin takes 9.2 seconds to fall. So now it's easy to figure it out. So if you kind of draw this on a timeline, so This is Linda. She drops a coin, and then at a time TL later, the coin hits the ground. And at some point around here, Terry also drops the coin to the ground, and then at the same time it also lands. Yeah, and this time is 9.2 seconds for the coin from Terry to land, and the coin from Linda to land, it took her 13.0 seconds, and this is 9.20. Then how long afterwards, after how long after Linda drops her coin should Terry drop his coin? That is we are interested in this time. Yeah, that is actually TL minus TT. And how much is that time? That is 13 minus 9.2, and that gives me 3.8. So that is, so Terry must drop his coin 3.8 seconds after Linda, if he wants his coin to land on the ground at the same time as the Linda's coin. There's another question. What would be the speed of Linda's coin as it reaches the ground? This one is not particularly difficult because we have done something like this earlier also. So it starts at u is equal to 0. I'm interested in finding v, the final speed, with an acceleration of constant acceleration of 9.81, and the distance it has to fall through was 830. Yeah, 830 meters was the distance. Okay, so I'm interested in finding v. So I can now use make it some space. So v is equal to sorry, I can't use that one. So notice that I can also use the new time that I found for Linda's coin. I know the t, I know the time it takes for Linda's coin to fall, so I can use that also. But generally it's a good idea to always stick to values that they have given in the question as much as possible, and only in cases where you can't find something to include the values that you calculated, because if you make a mistake in one of your calculations, that mistake will propagate every time you use one of your values. So as much as possible, try to stick to values that are already given in the question. So even if one part of your question is wrong, the next part of the question won't be wrong. So here, even though I could use the time it takes for Linda's coin to fall, which I calculated earlier, and then I can use v is equal to u plus at, I'm not going to do that because that is not a value that was originally given to me. So I'm going to just use these values, and I'm going to use v squared is equal to u squared plus 2as. So I get v squared is equal to u squared plus 2as. So that means it's u squared is 0 plus 2 is 9 point plus 2a, that is 2 times 9.81 times 830. Then v is equal to square root of that, square root of 2 into, I don't know why I do it so long, 9.81 into 830. And how much is that? 2 times 9.81 into 830, square root of that is 128 meters per second. That is a very, very, very high speed. Yeah, I think it actually works out. So 2 times 9.81 times 830, 2 times 9.81 times 830, square root of that. Yes, I think that's, I still get the same value, but it's unlikely that this will actually reach this value, for the reasons that I'm going to I've written down here. Yeah, so this question is not a very good question because we're making some assumptions that are very likely incorrect, but we did the question assuming these are true because it's an interesting question to do. So some of these assumptions are the ones here, and the assumption that I think the biggest assumption is that the acceleration is constant. That means it's falling freely without experiencing any other forces like air resistance. If a force like air resistance acts, then the acceleration is not going to be constant. It's actually going to slow down. So because of that, I don't think it'll actually reach 128 meters per second. It'll actually, I think it'll be much smaller than this value. And of course, we are assuming that the coin can reach the ground, but most probably it won't, because the building has like a bit of a wider base. So if you see a photo of the building, it looks a bit like this, it's not exactly like that, but the base of the building is large. So if you drop something from here, it'll probably just won't reach the ground. It'll just hit somewhere around here. Yeah, but we are assuming that that doesn't happen. Then we are also assuming that the person can get to the very top of the building, because from the photos I've seen, the top of the building is just like a little, I think the top of the building is just like a little just a little thing. I don't think a person can stand there. I don't know, from the photos it seems like it's a place that a person can't stand on. Also, assuming that people are allowed to actually drop things from the top of the building, which I don't think is allowed, because usually these kinds of buildings, there'll be some sort of a railing, and I don't think people will be allowed to even get into a back. I don't know, I'm just speculating here. But generally, when you go to a very tall tower, people are not allowed to go out into the like an open area. People are usually kept indoors. So I don't think this experiment, this thought experiment, is possible at all. But it's an interesting question. So yeah, that's why we did it. Yeah, so these are some examples of how to use equations of motion. Yeah, and next we also have to look at how to do questions where things are not just moving in a straight line. Like when you kick a soccer ball, at an angle to the ground, it's not going to go in a straight line. So that kind of motion, we call that a projectile motion. And the next part of the lesson would be to consider that type of motion. Yep, so that's the end of this lesson for now.